What is the law of conservation? Lesson 2, the law of conservation of energy. I've just done a big rant about how important it is. What is it? It says this: the total energy of a closed system is neither increased nor decreased in any process. Energy can be transformed from one form to another, but the total remains constant. The shorthand version is energy is conserved. When you say energy is conserved, what you're saying is the amount of energy before equals the amount of energy after. Although instead of before, we'll say initial, and instead of after, we'll say final. As an equation, it's written like this. I'll show you the derivation first of all. We said that work equals change in kinetic plus change in potential. What's change in anything? If we're looking at a closed system and you want to know the net work that was done, the energy change that occurred, that's the answer. What we're really saying, Curtis, is this. If you're looking at a closed system, if there's no other outside energy sources, you can't get energy out of it. The net work done is always going to be zero. Whatever you gain, you lose somewhere else. Whatever you lose, you gain somewhere else. If you add up the amount of work done, the answer is zero. Now, if you plus the negative K initial, KE initial, and if you plus the negative PE initial over, this is what you saw in Physics 11. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. This was the law of conservation of energy. But you can see, Claire, it pops right out of our work energy. Actually, you were away. Peter, you can see it pops out of our work energy theorem if we say, if you're looking at a closed system, no work is done. The only way you can get work to be done is if there's an outside energy source. But if there is not, energy is conserved. Or if we want to include friction, we can write it this way. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Mr. Dueck, you haven't changed anything. Okay, that's if there's no friction. If the numbers don't balance, if when you add up all of the energy at the beginning and you add up all of the energy at the end, you find out you have less energy at the end, what's missing must have gone into heat. Okay, Claire, and sound and other dissipative energies, but we said last day that we're going to say that heat is the work done by friction, just to simplify everything. We'll say everything goes into there. These two equations also not on your formula sheet, I don't think. I don't think conservation of energy is on there, is it? Under the work energy unit? No. So, sorry, I fibbed earlier when I said this was one equation. You had to there's a couple equations you have to memorize. Nate, you going to make it? You're live? Okay. I wrote here, Mr. Dueck has a good demo for this. You'll notice in the last couple of days, I set up the little ball rolly thing on my whiteboard here. Yep. Fridgets, if you go to Amazon. What, sorry, what? I didn't hear what you said. A Rube Goldberg machine? Patience, young grasshopper, patience. We'll get there. So, why is this so nice? What's the big deal, Mr. Dueck? The big deal is that energy is a scalar. And because it's a scalar, it doesn't care about the pathway. Example 1 says the projectile is launched into straight up into the air. If it reaches a final height of 93 meters, what was its initial velocity? You could solve this using dphyc, saying, VI equals question mark, D equals A equal, but we can also use work and energy to solve this. Here, I would probably not use work and energy because everything's in a nice straight line, but I want to show you that it works. And then example 2, for a roller coaster with a curvy path, we'll convince ourselves that it works there too. Generally, I ask myself this: is there a change in height? Is there a change in speed? Then that's probably a job for conservation of energy. That's my little mantra. That's my little question that I ask myself. So looking at this question, what are they asking me to find, Kieran? VI. Is there a change in height? Is there a change in speed? I think this is a job for conservation of energy. Although I could also solve this using kinematics, using VIT and a half AT squared, all that stuff. I can say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Plus heat. Does this question mention heat or anything like that, or friction? No, then let's assume we're in our magic physics world where there is no air resistance. We said last day that kinetic energy was a half mv squared. So kinetic energy initial is going to be a half mv initial squared. Plus, we said last day that potential energy with gravity was equal to mgh. So I think potential energy initial is going to be mgh initial. And it's going to be a half mv final squared plus mgh final. Oh, I noticed something. Do you see something that appears in every single term? What, Bree? There's a reason they didn't tell me the mass. Apparently the mass cancels. Or there's a reason in Unit 1 when we were looking at projectiles, I never needed to tell you the mass because the mass cancels. Are any of these zero? Is our initial liftoff velocity zero? Is our initial height zero? Ah. Is our final velocity at the top zero? Ah. Is our final height at the top zero? No. So after all this, we end up with a half V initial squared equals GH final. Kieran, what did you say they're asking us to find? Oh, you know what? Times by 2 to move the half over. And then how would I get rid of the squared? By the way, put your pencils down for 1 second. Look up. Yes? VF, according to this question, is 0. So I could minus this over and I would get negative 2AD. Yes? What's A? What's G? Negative 9.8, which would cancel out that negative in front and just leave you with a 2, and then square it by the... Can you see I've actually just derived that equation? You may recall at the beginning of the year that VF squared equals VI squared plus 2AD. Ashley, I said this is a tricky one to derive until we get to energy. It turns out it pops right out of this conservation of energy equation right here, for what it's worth. Pick your pencils up, please. VI equals 2, 9.8. Mr. Dueck, why didn't you put in negative 9.8? Energy is a scalar. Work is a scalar. No direction. Times 93. If I want to hit 93 meters high, what do I have to leave the ground at? What's my initial... And by the way, technically I found the initial speed, not the initial velocity, but we know it's straight up. What'd you get, Michael? 42.7. 42.7. Anybody else? Yeah? 42.7 meters per second. Here, Ashley, it's arguable as to whether conservation of energy is faster than using VF squared equals VI squared plus 2AD and just crunching the numbers. Okay, fair enough. But where conservation of energy really shines is roller coasters. You see, a roller coaster travels a curvy path to get to the ground. But because work and energy, Sam, are scalars, they don't care about how I got there. They just care about before and after. I will get the same answer if the roller coaster had just one big hill. I would get the same answer if the roller coaster had one straight line steady hill. I would get the same answer if the roller coaster went up for a while, came back down below the ground, went up for a while, and ended up. All it cares about is before and after. Let me try and convince you. So here we have the energy skate park with a curvy path. Not a nice straight line. And if I show you the bar graph of energy, now let me take this skateboarder. Let's give him a bit more potential energy. And you can see the total energy not changing. That's the law of conservation of energy. And you can see energy is being transformed from one to another. Where is the potential energy going to be the lowest? Now, here's the other nice thing about potential energy. I can put 0 wherever I want. So if I want to, I can move the ground mathematically right to there. And now at the bottom, I have no potential energy. It's all turned into kinetic. Energy is a scalar. It doesn't care. And Petra, that makes my math much nicer. Who cares how high I was? I'll just let that be ground level. Where will I have the most potential energy? At the top. Where will I have the least kinetic energy? Also at the top. That's when I come to a stop. Now, this is in our magic physics world where there's no friction. What if I add a little friction? What if I say that mu is not 0? Which energy bar is going up? What is energy being transferred into? See it? Heat, yes? Is the total energy changing? Nope. But because more energy is being lost to heat, I have less to go into potential and kinetic. That's why, for example, in a swing set, when you stop swinging, when you stop pumping, you'll gradually come to a stop. You're losing some of your energy bumping air molecules to air resistance and to friction through the chain. Okay? But here's the nice thing, Claire, even with a curvy path, We don't care. Energy is a scalar. That's where energy really shines. So let's go back and look at example 2. Example 2. Petra, what are they asking me to find in example 2, dear? That's a speed. Final or initial? What do you think, folks? Is it asking us to find V initial or V final? Bree? Final. Okay. Petra, do you see on a roller coaster, is there a change in height? You've been on a roller coaster. Is there a change in height? Yes. Is there a change in speed? This is a job for conservation of energy. Do you see what I'm... So last unit it was, what am I going to do? Free body diagram. Here it's going to be, one of the questions I'm going to ask is, if they're asking me to find something, is there a change in height? Is there a change in speed? Is there a curvy path? This is absolutely a job for conservation of energy. So I'm going to start out going like this, dear. Am I going to write plus heat, or how do I know not to add plus heat? Oh, it says ignore friction? Well, that's convenient. Are any of these 0? Let's see. Now, kinetic energy is a half mv squared. Is my initial speed 0 according to this question? Am I starting from rest? No. Am I starting out on the ground? Nope. Am I ending up coming to a stop? Nope. Am I ending up on the ground? Ah. This is going to be a half mv initial squared plus mg H initial equals a half m V final squared. Petra, what did you say we were trying to find, kiddo? Which is what in my equation here? Which of these variables is this? Did you say VF? Okay, yeah, I can hardly hear. Yes. Oh, is there an M in the first term, Petra? How about the second term? How about the third term? Have you been on a roller coaster before? Did they ask you to step on a scale before you got onto the roller coaster? You know why? Why, folks? Turns out, this is cancel. What did you say I'm trying to get by itself? Okay. You could divide by a half and then square root. Because I'm not a fan of fractions, usually what I do with this equation is I actually go like this. I actually go times by 2, times by 2, times by 2. Is that legal? Can I multiply everything by the same number? As long as I multiply everything by the same number, that's legal under equation solving. But why is that so nice? Because race 2 and a 1/2, 2 times a half, that's just a 1. And 2 times a half, that's just a 1. And I end up with this. The VI squared dropping down. The 2 doesn't cancel here. I end up with that. Put your pencils down. Mr. Dueck. Yeah, Michael. Didn't we just derive that equation? Sorry, I forgot the square. That's where that equation comes from. So again, in the beginning of the year, somewhere around lesson 4, when we did the 4 kinematics equations, I didn't derive this one because I said, it's way easier. It just kind of pops out of conservation of energy. There it is again. VF squared equals VI squared plus 2AD. Nerd moment over. Pick your pencils up. Petra, what did you tell me they're asking us to find? I have VF squared by itself. Hey, how to get rid of a squared? Did you say square root? Because you would be right. It's going to be... So, the final speed at the bottom of the hill is going to be equal to 22 squared plus 2, 9.8 12. (22 squared plus 2, 9.8 times 12, square root, 26.8 meters per second. By the way, how fast was I going at the top of the hill? 22. If I go down a hill, do I speed up or slow down? So this looks about right. I was expecting an answer bigger than 22, but it's not a really high hill, so I was expecting an answer a little bigger than 22, but not crazy bigger than 22. Is that okay, Peter? Good stretch? You awake? Example 3. A 14-kilogram object is dropped from a height of 40 meters and it strikes the ground with a speed of 25 meters per second. How much heat energy was produced during the fall? Hey, Josh, what are they asking me to find here? Sorry, what? You know what? Is there a change in height? Yeah. Is there a change in speed? This is a job for conservation of energy. Did they talk about heat? Then I'm going to use this one. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final plus heat. And strangely this time, Josh, you know what I'm trying to get by itself? Heat. But before I do that, are any of these 0? What does the word dropped mean? If I drop something, what's its initial speed if I drop it? 0. So what's its initial kinetic energy if I drop it? I think I can say that. If I drop something, is its initial kinetic energy 0? Sorry, is its initial potential energy 0? No, it's not on the ground. When it hits the ground, is its final kinetic energy 0? And I got to be careful. After it hits the ground, yes, I agree, its final kinetic energy is 0. But as it hits the ground, is its final kinetic energy 0? No, it's hauling. When it hits the ground, how high is it?
0.
Oh, so what's the final potential energy? I can do that. Yes? Hey, Josh, how would I get the heat by itself? Yeah, it just looked ugly at first, but actually it turns out to be not too bad. I think we're going to get this. How much heat? That's going to be the amount of energy you started with, take away the amount of kinetic energy there was at the end. Whatever's missing went into heat. Heat equals mgh initial minus a half mv final squared. Hey, Jordan, is there an m in every single term this time? Say no. Oh, you did say no. What term doesn't have an m in it? Okay, if we start looking at friction, then the mass doesn't cancel. So, Petra, technically on a roller coaster, your masses don't cancel. Although, do they grease roller coasters down pretty good? Do they? So do they reduce the friction as much as possible on roller coasters? So you know what? For all intents and purposes, Michael, your masses do cancel because they're nearly frictionless. They don't lose very much. Hey, mass 18, 9.8, 40, plus a half 18, 25 squared. How many joules of heat energy were created during the fall by bumping into air molecules and by hitting the ground? Yep. It's supposed to be a minus, Mr. Dueck, a minus. Thank you, Nate, my friend. That would have been a disaster. Candy for you later. 18 times 9.8 times 40 minus 0.5 times 18 times 25 squared. Do I need to square root here? No. Is that right? 1431 to 3 sig figs, 1,430 joules of heat. Energy is conserved. Example 4. Example 4. Kelly, what are they asking me to find in example 4? Before that, first phrase, first 3 words. What are they asking me to find? Work. Oh, that's easy. Work is equal to what times what? Force times distance. And do you see a force in newtons or a distance in meters anywhere in this question? Sorry. Oh, that's still easy. Work is the area underneath the force versus distance. Do you see a graph in this question anywhere? Sorry. But we have our third definition of work, what I call the work energy theorem. And it says, hey, you want to know how much work? Is there a change in speed here? Yeah. Is there a change in height? No, this is not a job for conservation of energy. Also because they said how much work. So I'm going to use change in potential and change in kinetic. Hakeem, is there a change in height? So is there a change in potential gravitational energy? Is there a change in PE initial? You know what? I think I can say, since we're on level ground, nothing. And Hakeem, what's change in anything? So this is going to be a half mv final squared minus a half mv initial squared. Yes? Yes. Oh, now it's kind of plug and chug. Work is going to be 0.5, 1,200. Oh, wait a minute. Oh, no. Got a problem. What's my problem with my speeds? They're in kilometers per hour. How do I go from kilometers per hour to meters per second? It's something to do with a 3.6. Divide. You know what? I'm going to be really lazy. I'm going to go bracket. What's my final speed? 50 divided by 3.6, close bracket, all squared. There's V final squared minus a half m 80 divided by 3.6 all squared. Hey, there we go. That should work. Hey, do the massives cancel this time? Is there an m in everything? Not in work. Or let me ask you this way. Would it take more work to stop a semi-truck that's at 80 going to 50 kilometers an hour than it would take to stop a smart car? Yeah. The masses shouldn't cancel. It would take way more work to stop a semi-truck compared to a smart car. Or slow one down, as in this case. So this is going to be 0.5 times 1,200 times bracket 50 divided by 3.6, close bracket. Whoop. Squared. Minus 0.5 times 1,200 times bracket 80 divided by 3.6 squared. Do you get negative 180, 55, well, that, double check me, I could be wrong. I don't think I am. But I could be. A divided by 3.6 all squared. 50 divided by 3.6 all squared. What's with the negative, by the way? What's that telling me? What can you say about the vehicle?
It's slowing down.
It lost what?
Energy.
Yeah, it's slowing down, but specifically in this, because we're talking not in terms of speeds, we're talking in terms of work and energy. Negative work means the vehicle lost 1/8. You know what? It's going to be this. Work equals 1.81 times 10 to the 1, 2, 3, 4. Equals 100 negative, Mr. Dueck. Don't forget the negative. It equals a negative 181 kilojoules, if you wanted to answer it that way, for that matter. Hey, Kelly, what was the second question I asked in this question? What force does the work? We talked about this the other day. When you hit the brakes on your car, what force is doing the work? Friction. What if it's icy? Why is that a problem? Friction's so small, it can't do enough work to bleed off your kinetic energy. Sorry. So what force does the work? B. Friction. C. Hey, where do you think, if this energy, Mr. Dueck, is transferred, is conserved, where do you think the energy, the kinetic energy from the car is transferred to? I heard it. Someone said it. Heat. Heats up the brake pads considerably. In fact, for big trucks, when they come to a hill, what do they do for big semi-trucks when they come to a steep downhill? Pardon me? Why do they gear down? They want to lower their kinetic energy. The energy's got to go somewhere. Why not avoid picking up that energy in the first place? Why not? Anybody here drive a Prius? Or have their parents drive a Prius? So one of the neat things about the Prius, it has what they call a regenerative braking system. What they do is, rather than having the energy go into heat, they bleed the kinetic energy off, but they have it go into charging the batteries. And literally, what's slowing your car down is not friction on the brake pads. It's your battery. It's the cars, as it comes to a stop, the wheels turn into generators, and they literally have to force electrons through a resistor to charge a battery. And the pressure of forcing those electrons requires a force, and you're applying it over a distance. It's a work force times distance. It's bleeding off the energy. It's a neat little system. Very clever. How are we doing here? Oh, we're getting there. Example 5. A 12.5 kilogram object is pushed across a level floor with a coefficient of friction of 0.35 for 6.4 meters by an applied force of 58. You know what? I'd better dope. We have an applied force of 58 newtons. Mu is 0.35. Friction. Gravity. Normal force. I don't think this is a lawnmower question. I'm pretty sure mg and Fn are the same. Okay. Cliff, what's part A asking me to find?
How much work is done by the applied force?
Well, the first thing I always look at is work equals force times distance. Did they give me an applied force?
Yeah.
Did they tell me the distance that it's being pushed?
Yeah.
Well, hey, it's a straight plug and chug. Even you could get, I mean, that came out wrong. 58 times 6.4. Cliff, how much work was done by the applied force?
371 newtons.
371 newtons?
I mean joules.
I think you mean joules. right? Except, Cliff, not all of that goes into making this box speed up. How much work is done by friction? Well, let's do friction in red because it's heat. Work equals force times distance. What distance? 6.4. What force? Friction. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force, and this time it is mg. Hasn't been that for a while, but this time it is. So the amount of work done by friction is going to be 0.35, 12.5, 9.8, 6.4. 0.35 times 12.5 times 9.8 times 6.4. Do you get 274.4? Yeah? All right, 274. Cliff, 274 what? Joules of work. And we're wrong. Why are we wrong? Because we are. Why negative? What direction is the force? Forwards. What direction is the, to the left? What direction is the movement? To the right. What's the angle in degrees between the force and the motion? Remember we said actually it's technically force times distance cosine theta. So I've told you I'm not going to give you stuff on components this unit because I really flogged that to death last unit. All you're going to have to remember is if it's in the opposite direction, make it negative. And what's the negative telling you? You lost energy to friction. What's the net work done on the object? What was the total work done by the applied force, Cliff? Part A?
371 joules.
Did all of that go into speeding up the block? No. How much of that went into friction?
274
Hey,
joules.
what's the net work done? What's left? It's going to be the work done by the applied force, take away the work done by friction. Now, I got to be careful. Is friction negative? Sorry, is the work done by friction negative? Was the work done by friction negative? Yes. Technically, I should say you add them together because you're adding a negative. If I write this, it's technically a minus minus, but I've learned over the years, kids think this, understand this better. This, oh, how much work did you do? Take away whatever you lost to friction, and they don't go minus minus. They clue in. It's going to be 371, take away 274, not take away 274. Nevi, okay with that? So this is clearer. Even though for the math to work, I should say you're combining and you're adding them, but that's because we called friction a negative force, and we said you're losing energy. 371, was it exactly 371? 58 times 6.4, 371.2, take away 274.4, I get 96.8? Joules. That's what went into the block. So if the block gained that much energy, what happened to it? How did it gain that energy? What form did that energy take? How was that energy transformed as it entered the block? What form did that energy go into? Heat was friction. Took care of that. Where did this 96.8 go? What did it do?
Push it.
Did you hear? Not just push it. Here's the key. Speed up. It's increasing kinetic energy. That 96.8 is going to go into the kinetic energy of the block. That block, when we're done, is going to have 96.8 extra joules of kinetic energy. It's going to be going faster. Which we also know because you're applying an unbalanced force, it's going to accelerate. That was last unit. But Manisha, we're saying there's another way to think about it in terms of work and force and distance. You can say it's gaining energy coming from somewhere. Which means if we assume the object started from rest, we can calculate its final speed. Really, Mr. Dueck? Yeah, really. Because we could also say our third definition of work. We could say that work equals the change in potential plus the change in kinetic. Race, we could say we're on the ground, level ground, so the change in potential ain't happening. And what's change in anything? So we could say this: work equals KE final minus KE initial, except the fact that it says from rest, Race, why does that mean I can do that? VI was 0. How much work was done on the object? What did we say the net work was? 96.8 FM. That equals a half mv final squared. How would I get the v final by itself? Eventually square root, but not first. What am I going to do first? Times by 2, divide by m, square root. V final is going to be big square root times by 2. There's the 96.8. Divide by, what was the mass? I've turned the page. Sorry? 12.5? Try that again, Mr. Dueck. Here we go. 2 times 96.8 divided by 12.5, square root of that. It's going to be going 3.9 meters per second, 3.94, 3.9 meters per second. E, I wrote calculate the final velocity of the object after 6.4, I forgot the meters. Using kinematics, we could. I would find A, VI is 0, D equals 6.4, find V final. We could get all that. Meh. Example 6. How much am I going to get through today here? Boy. Okay, we'll see how far we get. Example 6. Meh. Example 7. What are they asking me to find here in example 7, Peter? A force. Peter, read this question very carefully. Is there a change in speed? Yeah. Is there a change in distance? Well, it says 12 centimeters, so there is a distance. I think they're talking about force. There's a change in speed. They mention a distance. This is a job for work because there isn't a change in height. What do I mean by that, Peter? I think I would use the work energy theorem. You with me, Peter? Hey, why can I do that? I don't think the bullet mentions a change in height. Does it? Traveling horizontally, yes? We're assuming, but doesn't say anything like else, so yes? Okay. So this is going to end up being KE final minus KE initial. Change in anything. What did you say they're asking us to find? Anybody see a way that we can get a force to show up in this equation? Oh, work is equal to force times distance. Now we're using two different definitions for work. What can I do that? It's coming to a stop. So if I look at this all now together, it looks like I have this. Force times distance equals mv initial squared over 2 with a negative, whoop, that looks like it's part of my equal sign, with a negative in front of it. I wrote it over 2 instead of a 1/2 in the front because I think now I'm going to start to move stuff around and I wanted 1 fraction equals 1 fraction so I can move things diagonally. Peter, what did you say we're trying to find? How did I get the force by itself? Oh, so now we're doing some ballistics analysis here. The average force is apparently going to be negative mv initial squared all over 2d. Negative, what's the mass? Don't say 20, because it's not. Right, 20 grams is 0.02. 250 squared divided by 2. What's the distance? Don't say 12 because it's not. .12. Negative 0.02 times 250 squared divided by bracket 2 times 0.12. Average force required to bring a bullet to a stop? Negative in the opposite direction of motion, 5,208 newtons, or 521, negative 5210 newtons. What did we just find? Force. Newtons. You'll find it's worthwhile memorizing what units go with what. It really is helpful. It really makes things easier. Okay, how much further am I going to get, Mr. Dueck, here? We got Tarzan, we got... Okay. Pause here. Give me a second. We're going to pick up with this next day, but if you want to get a head start on some of the homework, this is what I'm eventually going to assign, but I haven't done every single blatant example like this. I am going to assign number 1. Now, where it says part A, write a work energy equation, I'm not fussy if yours looks a bit different from what my friend who typed this up wrote. He tends to teach everything in terms of work. He doesn't actually use the conservation of energy equation. So I'm going to say also number 2, where it says write a work energy equation, probably yours will look like the one after the word or. Anyways. Number 3 is good. 4 is good. 6 is good. 7 is good. Okay. That, if you want to start, but I'm going to give you time on Wednesday. I am going to be also finishing off this lesson, starting off the next lesson, and then Elijah wants me to show you some nerdily cool little videos because he's all a quiver. So, okay, we will.